Okay, we have a very important topic today. It is RSA. So it is explained in many books, which is about cryptography or for some reason blockchains, although almost no cryptocurrency uses RSA. Every Bitcoin book talks about this because they think that public key cryptography consists of only RSA. But it is only one algorithm, and generally, we prefer elliptic curve cryptography instead of this. So before explaining RSA, and I'm going to explain its basic version on a single slide, but let's see some elementary number theory to see why this works, okay? So let n be an integer, then the number of positive integers that are less than n and relatively prime to n, in other words, greatest common divisor of n and c for any number that is less than n, should be 1. And the number of all of these numbers is given by phi n. So this is Euler's phi function. So phi n means that number of integers that are relatively prime to n, and there should be also less than n. For instance, that n has prime decomposition. So we factorize it into primes. Of course, it has to be consist of primes and maybe some powers of it. So this is why we have AIs on top of it. For instance, 12 is 2 to the 2 times 3, okay? Then phi n is actually multiples of these phi pi AIs, okay? So instead of trying to calculate this, you can go and calculate these independently. Then you will ask, okay, then how can I find the phi pi AI, right? Now I only know that p is a prime number. So there's also a formula for that. Phi p to the k is actually p to the k minus p to the k minus 1. Let's think about the scenario where k is equals to 1. And let me give you a simple example where p is 7. So phi 7 is 7 to the power 1, right? Minus 7 to the power 0, which is 1. So it is 7 minus 1, 6. Actually, if you only put a prime number p here, it will be p minus 1. Because think about the prime number. Anything less than it has to be relatively prime to itself. Otherwise, it cannot be prime. That is the whole idea. So this way you can calculate phi. So it is not that important actually, but at some point I will use it. But just you know that there is such a Euler phi function, okay? And let's also talk about some theorems. This will be useful when we talk about checking if a number is prime or not, okay? Although these are important terms, it is very easy to put it on the screen. So Fermat's theorem is as follows. Let p an odd prime number. A to the p minus 1 modulo p should be congruent to 1. A very nice theorem and good to know. Euler's theorem is a little bit more general than that. Now I can divide p minus 1 by 2. But this time result is not 1, but it looks like a over p, but actually I'm using Legendre symbol here. And this Legendre symbol gives you either 0, 1, or minus 1, depending on these scenarios. If p divides a, the result is 0. If a is a square in fp, then it is 1, minus 1 otherwise. So this gives you a little bit more info, let's say. And this will also, I will use it when I'm checking a number is prime or not. Corollary is a to the phi n modulo n is 1. So actually, I'm not proving it here, and it may not be directly easy to see it, but you know, think about prime decomposition of n, and you know, think about Fermat's theorem, and you know, use it repeatedly. This will be the result. RSA works because of this. This is why I'm showing it, okay? A to the phi n. Recall that phi n is the number of integers that are less than n and relatively prime to n, okay? So this is a very nice corollary. Again, it is basic number theory, but I'm not going into proofs. Let's go to RSA and see how we use this. Key generation. So RSA works like this. Initially, you have to choose big primes P and Q. So the question will be, how big should they be? At the end, I mean, in the next step, I will multiply P and Q and obtain N. And I would N to be a number that is at least 3072 bits. This is how large P and Q should be, okay? Because their multiplication has to be 3072 bits. In that scenario, you get 128-bit security. So if you want military-grade security, this N has to be more than 15,000 bits. So here we are dealing with very huge numbers, right? But let's see the pseudocode. We randomly choose two big primes, multiply them, and say that this result is N. Then I choose a number E, which has to be between 2 and N minus 1, such that E and phi N has the greatest common divisor 1. So they have to be relatively prime. But recall that phi N actually equals to, due to prime decomposition, phi P times phi Q, right? And since these are primes, this number is P minus 1 times Q minus 1. Let's recall the formulas I said. So you have to choose an E that has to be relatively prime with this number. And this is generally chosen as a very small number to have speed up in the computation. So if 3 is relatively prime with this number, then you can choose E equals to 3. Okay, as simple as that. Sometimes it's a choosing 2 to the 16 plus 1, so that the computations are really fast too. Okay. So next step. Now that you chose an E, calculate D. And D should be E inverse modulo phi N. Okay. So you might just ask, okay, phi N now is a very huge number. How can I find the multiplicative inverse of D, right, in modulo phi N? And there's an extended Euclidean algorithm which you can easily do this. So this is really fast. Okay. Regardless of the value of E, and it doesn't matter how big phi N is, you can calculate this. It is not that hard. And you need to do this only once because we are doing it a key generation, right? So this will be only done by once. As you can see, the steps are really simple. Now we have done actually. Now your public key is N, which is the multiplication of these two primes, and E. Okay, so N is referred to as RSA modulus, and E is referred to as RSA exponent. Okay, so if these are public parameters, then what is the private key? Your private key is D. But phi N, in other words, P and Q has to be also kept secret so that you can, keep working and nobody can listen to you. I mean, if you tell other people what P is, then all security is lost. Let's see how this works, because this is the key generation, and I explained the steps, but let's see how we use this public key and private key during encryption and decryption. So let's look at encryption. This is really simple. Somebody wants to send you a message M, and M has to be less than this modulus, otherwise information will be lost. So you have to, kind of divide your message into some pieces, right? So think about it as if we are working like a block cipher, but it depends on the padding and so on. But here I'm only explaining its basic form. So I have a message which is less than M minus 1. What I do is I calculate the E power of M modulo N. And the result is ciphertext, and I give it to everybody. Sorry, when somebody wants to send me a message, they use my public key, they encrypt their message and send it to me, okay? So anybody can send me a message because everybody knows my public key because I publicly announce it. But only I should be able to decrypt it. So how I do the decryption? I receive the ciphertext C, I calculate the D power of it modulo N. Recall that D is the private key, so I obtain M back. So you will say that why this is the case, because due to it, let's go back. If you use these theorems and obtain this corollary, actually this leads to it, okay? Because think about it, C is just M to the E, right? So at the end, you have M to the E times D modulo N. So due to this property, actually, E times D will give you 1 at the end of the day, modulo phi N, okay? So where the security lies, so anybody capturing C they already know E and N. So if they can solve the discrete logarithm problem, they can capture the message, right? So the message security actually relies on discrete logarithm problem here, not the factorization problem. But then this is only for factoring a single, obtaining a single message, right? If you can solve the discrete logarithm problem, you can listen any message, you can decrypt, right? But there's more security here. How can I capture the private key? And in order to do this, you have to calculate inverse of E, but you don't know this modulus phi m, which is P minus 1 times Q minus 1. So if I can factorize n, I will obtain P and Q. So I will obtain phi n. So I can also use the extended Euclidean algorithm to compute D and obtain the private key, right? So this is done as simple as that. So message security depends on the discrete logarithm problem, but the whole RSA security, your secret key security, depends on the factorization problem. So if you have a fast factorization algorithm, just since n is the public parameter RSA modules, factorize it and capture the secret key. As simple as that. So why decryption works? Think about the scenario where the greatest common divisor of m and n is the modulus, we call this 1. So the message you want to send me is relatively prime to n. And this is generally the case, okay? So what we do is, recall that when I obtain the C and take the D power of it, I actually end up with m to the E times D, right? M to the power E times D, actually 1 plus K times phi m, because, this is obtained, D obtained is modulo, inverse of E modulo phi m. So if you take this m to the 1 outside, you end up with m times m to the phi n, bits multiplied with some constant k, okay, power to some k. But again, by the corollary I showed you, this is 1. 1 to the power k is 1, so you end up with m. So what happens if in the second case where the greatest common divisor of these m and n is not 1? So for some reason, think that, for instance, the message you send me, you are so lucky that you chose m equals to be q, my secret prime, one of my secret prime numbers, right? Let's look at the scenario where p does not divide m. Then m to the ed modulo p is again like this, okay? You do this by Fermat's theorem. It is m modulo p. Now I'm working on modulo p, not m. That is the difference, okay? But if p divides m, then m has to be 0 modulo p. Again, m to the ed should be 0. M to the ed should be equal to m because 0 equals to 0 modulo p, right? So do the same thing with modulo q. In both cases, since you have m to the ed equals to m modulo p, similarly, you will end up with m to the ed equals to m modulo q. In that scenario, now we can use Chinese remainder theorem, and you end up with m to the ed equals to m modulo pq. This is why decryption works all the time, okay? Again, if you're interested, go into details and see the number theory works really nice here, okay? So it looks really fine. It looks really simple, but now I'm actually making I'm creating a paradox here. I'm saying that factorization is not easy, right? So this is why I say that whole security depends on this, n times n equals to p times q, and you cannot factorize it. I'm saying that this is a hard problem. But then at the first step, I initially say that choose big primes and p and q. If you know factorization is hard, how can I randomly choose big primes? How can I be sure that it is random? This actually leads us to the main question I explained at the beginning of these slides, where I mentioned that a search problem sometimes harder than the decision problem. Factorization is hard, but saying that if a number is prime or not is not that hard, okay? As I mentioned, we have sub-exponential algorithms for factorization, but we have polynomial time algorithms to check if a number is prime or not, okay? So let's first talk about it, but we are not going to use that algorithm anyway, but let me explain. Yes, parameter selection for RSA. And actually, this will lead us to primality testing, right? P and Q should be generated randomly. In standards, a random number generator, which is a combination of physical random number generator and the deterministic random number generator, is used most of the time. So we talk a full lecture about randomness. So please remember all of those arguments we made there and assume that you have a random number generator. So if you randomly select an odd 512-bit number, it's prime with probability 1 over 355. So you should be very lucky to pick a odd number, very huge odd number, and expect it to be prime. And this probability decreases when the number increases, right? The size of the number. So then what you need to do is to apply primality test to this number and check if it is prime. So what you do is, for instance, if you need a prime number which has a size of 512 bits, you pick a random odd integer of this size, then apply primality test and check if it is prime. If not, pick another one. You continue this way until you find two primes, and you name them P and Q and use it. So primality testing, as I mentioned, we have a polynomial time algorithm for testing primality, AKS algorithm, due to the authors Agrawal, Kagal, and Saxena. So it was a huge breakthrough, but it turned out that this is really slow in practice, although it is polynomial time, because you do a lot of computations and the sizes are big. So actually in practice, we don't use it. So then what do I do? The randomized polynomial time algorithms are used instead. So let's see how this works. Before actually also seeing those randomized algorithms, let me give you two more definitions about algorithm types. Some algorithms are referred to as Monte Carlo algorithms. A yes-biased Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is incorrect with a probability at most epsilon. So all of the primality testing algorithms will be Monte Carlo algorithm, and it will be yes-biased, meaning that when I give a number to this algorithm, when it says that it is not prime, it is correct all the time. But if it says it is prime, it will be prime with probability 1 over 2 or something, okay? There are also other types of algorithms. We are not going to talk about this, but you may be, experience it in real life scenarios when you write your code. A Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct if it finishes. Sometimes it does not, right? Let's focus on our Monte Carlo algorithm. So the first one is Fermat test. This is why I actually show you the Fermat's theorem. Given odd n, choose a random number a, okay? And check a to the n minus 1 modulo n and see if it is congruent to 1. Recall that we said that if n is prime, Fermat theorem says that this is always true, right? So if this is not equals to 1, then n is definitely a composite number, because Fermat's theorem says that if n is prime, this has to hold for any a. So if it doesn't give you, then it is composite. So a Monte Carlo algorithm, which says that this is composite, it is true all the time. But if the equality holds, then the test outputs prime, but this answer true with some probability, right? Maybe you were just lucky. N was a composite number, but you pick a value a, just by chance, a to the n minus 1 is congruent to 1 modulo n. Okay. A similar test, this time I will use the Euler's formula. You do the same thing, you randomly choose a, but instead of looking a to the n minus 1, what you do look at is a to the n minus 1 over 2 and check the Legendre symbol. So if it is equivalent, then n is definitely a composite number. If equals, the test outputs prime, but this answer is true with probability less than 1 over 2. So, it is, you cannot simply rely on this test, right? You do it and you rely all your security on this choice, but you cannot use this test and say that, okay, it is prime with probability less than 1 over 2. It is a small probability. Miller-Rubin algorithm actually combines these two ideas, so I'm not going into detail, but the when you combine both of them, the answer composite is definitely correct, and the answer prime is false with a probability less than 1/4. Okay? So if the test answers m times n is prime in succession, then the probability that n is composite is less than or equal to 1/4 to the n. So idea is as follows. You are given an n, odd number n, and you want to check if it is prime or not. I told you that pick a number a, check this. But if it works, choose another a, repeat the test, choose another a, repeat the test. Repeat this m times. And if in all of these tests, if it passes, then the number n is prime with it is prime with probability higher than 1/4/n, or 1 minus 1/, it is composite with probability less than or equal to 1/4 to the power n. So if, for instance, if m is 25, this should be 1/2 to the 50, right? So you should be very, very unlucky that if you repeat this test 25 times, and the test says it is prime in all of the 25 times, but in reality, it is composite. So this has a probability of 1/2 to the 50, which is a very small probability. Okay? So this is how you check if your prime, the odd number you pick is prime or not. And the thing is that we don't know if the implementers do this correctly, right? In most of the scenarios where you create a certificate or you do this kind of operations, your public and private key is randomly generated by these algorithms, right? So when they choose n, we have to be sure that they pick 2 primes p and q. So actually you can, collect RSA modulus of other people and check if they are prime or not by repeating these tests and so on.